Okay, physical science time. Today is this thing on? Is the little bar filling up over there? Zach, can you see if that little, on the lower right is a little microphone bar? Is that going up and down with my voice? Okay, thank you. Today tea drinker, physical scientist, lover of electricity, David Keim, I'm going to tell you about electricity. Why is it called the electric city? Probably because of all the electricity. You get my reference? Yeah, shut the door. Just shut the door. I wish no one in the world had ever heard that. Okay. Let's start with this. The objective reads, evaluate patterns of change in the electromagnetic force. Evaluate. Well, that's not working. What does the verb evaluate mean? Kind of, yeah. Evaluate change. Was it evaluate patterns of change? Well, it just says change now. In the electromagnetic force. Evaluate patterns of change in the electromagnetic force. What does evaluate mean? What's the root word of evaluate, if you had to guess? Almost, value. So to evaluate something is to tell the value of it, or to tell what are the things about it. Values are kind of like, we might say in science, properties. And so to evaluate, to tell the properties of, or to tell the concepts of patterns of change in the electromagnetic force. So electricity, you will understand from the way words works, is part of what of the fundamental forces. Do you remember the 4 fundamental forces of the universe? We've listed them before, I believe. Let me list them for you again, because it seems like I'm getting either wrong answers or blank answers. In order, and I may have forgotten to tell you this before, so in order from the strongest, that is the greatest force, to the weakest, the lowest magnitude of force, they are the strong nuclear force. That's a good name for the strongest force of the universe, is just straight up the strong force. The second one is electromagnetism, followed by the weak nuclear force. Can you guess what the weakest one is? I am the weakest one. Yeah, I contribute to this one. Gravity. Yep, you got it. Nice job. Gravity. However, in addition to being ordered on this list from strongest to weakest, they're also in reverse order, the longest range. What's the range of gravity? Yeah, it's universal. I mean, and I should say, they're all technically universal. They're technically infinite in range, but they all, at least gravity and electromagnetism, which we're going to talk about today, act on the principle of the inverse square, where the further away you get, not only does the force get weaker, but it gets weaker as the square of the inverse of the distance, which means that if you get twice as far away, it's now a quarter as strong. If you get 5 times as far away, it's 1/25 as strong. And so they drop off really fast. But gravity has the longest range, and the strong nuclear force has the shortest range. So there's a trade-off. Gravity kind of governs the way things are structured, the patterns of things on the cosmic scale, solar systems and galaxies and planets and things like that. The strong nuclear force governs the structure of things on what scale? Can you guess? The atomic, the subatomic even, the neutrons and protons and atoms and the like. But we're talking today about electromagnetism. We're specifically talking about electricity, which is part of the electromagnetic force. Can you guess which part? The electro part. The word electra, I'm probably going to mess this up. Comes from the Greek for amber. There's a... How do you think the ancient peoples, the ancient Greeks, for instance, might have recognized electricity? There's a really easy way, lightning. Yeah, how else? One other way that comes up in your lives that isn't like, yeah, exactly, static. And so the reason it's named after amber is that it was discovered that the hardened resin of ancient tree sap, amber, you know about amber, I think, right? If it's rubbed on a cloth, will cause that the piece of amber will be charged, and it's really prone to static electricity. And so that phenomenon was named after amber. And then we get things like electricity, electromagnetism, the electron, all of that stuff kind of stems from the idea of the static electric force. And that's the first thing we're going to talk about is static electricity. There are two kinds of electricity. The first one we're going to talk about is static electricity. What is static electricity? Electricity that does what? What's the root of static? Stays, yeah. Electricity that stays, I'm going to put that in quotes because it's kind of unprofessional, stays on a surface. It's like a gathering of electrons. The particle that mediates this is the electron, which we abbreviate, we'll need this later on in the year, with a lowercase e with a negative charge up in the corner. So it's a gathering, I'm going to put that in quotes too, gathering of electrons on a surface. You know the thing where if I gather up some electrons, it didn't actually work, but if I gather up some electrons with neither the floor nor my shoes are right for this, but if I gather up some electrons, as the ancient Greeks did with a cloth and some amber, if I gather up some electrons, I can cause an electric discharge, a static discharge, because I have gathered up some electrons on the surface of something. That's how static charges. And in fact, I haven't read this article, but I read the title of the article that sometime just in the last like 6 months, it was kind of either discovered or rediscovered or reevaluated the way that static electricity works. For a long time, it was a real mystery. Like, how is this thing actually occurring? And there have been fairly recent at least, articles published about the way that the static electric force functions. Another thing about static electricity is that we can induce charge, which means cause something to, I'm going to stop putting things in quotes, cause something to be charged, something to take on a charge. If I have the example from the 8th grade science text is if I have a flagpole here, and there's a big old thundercloud. I mean, that's not that big compared to a flagpole. As clouds go, that's not a very big one. But if the cloud has taken on a largely negative charge, that's what I'm trying to draw a little negative charge there. This is a mostly negative charge, right? In its normal state, matter, well, I shouldn't say in its normal state, but in the most usual state, matter is made of roughly equal positive and negative charges, right? So things are generally electrically neutral. If it has 10 quintillion positively charged protons in it, it has roughly 10 quintillion positively or negatively charged electrons, and they balance out. It has no net charge. Does that kind of make sense? But for some reason, we'll talk about that in a second, this cloud has taken on a negative charge. It has a mostly negative charge. How might it do that? How might the cloud take on a mostly negative charge? Yeah, maybe not friction, but the rubbing of this cloud basically on the surface, right? The cloud is not, as in my drawing, a discrete individual lump of atoms. In reality, what would you say? It doesn't have a well-defined boundary. And so as this whole mass of air moves over the ground, just like my feet moving over what would be carpet, it picks up a negative charge. And this flagpole, which starts out as mostly, or as neutral, right? Positives and negatives all mixed together. Roughly, this is not a very good drawing, but the flagpole has a roughly equal number of positive and negative charges, mostly neutral. When this negatively charged cloud comes along, what's going to happen to these negative charges? What's true of the same charges? Similar charges do what? No. Similar charges, or the same charge, What do? Oppose. They repel. So these negatively charged, or this mostly negatively charged cloud will push away the negatively charged particles in the flag. Where will they go? They just vanish? No, they get pushed down into the ground. So the ground takes on a more negative charge too. That's another thing, is there's an idea of conservation of charge, where the charge that makes up this can never be destroyed. It can move, but it can't ever be destroyed. But now we have, because of induction, because the charge has been induced in this flagpole, that process is called induction. A charge has been induced in the flagpole. We have a positively charged flagpole and a negatively charged cloud. And now what's going to happen? Thunder. You remember that from Encanto when the husband says, thunder, and then the wife says, are you telling the story or am I? But this is, thunder happens. Do you know what happens if I do this? Yeah, what? Say it, what I just said. It's thunder. I mean, you didn't hear it because it didn't actually happen. But you see the lightning, and you can recognize that's lightning, and you can also hear it. That little tiny noise is thunder. It's just on a smaller scale. And here's another thing, that thunder and lightning are one phenomenon, right? The really pedantic second grader will say something like, well, lightning is the thing you see and thunder is what you hear. And that's a nice distinction. They are one thing. They are one phenomenon. Lightning and thunder are one phenomenon together. And it's also the same phenomenon as that static discharge. So that's static electricity. The movement of charges kind of as they stay on surfaces. Does that make sense? Do you have questions about static electricity? We did some work with this last year when we had the balloon I rubbed on my hair, and we did some experiments of it. I think it's a pretty good video. But there's a video from me telling you guys about that in the lab last year that you can go back and watch. But do you have questions about static electricity? It should be mostly review. Okay. The other kind of electricity is, I'll just label that one also, current electricity. And this is if static electricity was how electrons behave when they stay on a surface, how might we describe current electricity? Yeah, the flow of electrons, the movement of electrons. And from your lab, what is the main way that human beings have come to use this? By building what? Yeah, wires, lights, that's all stuff. But the idea of how we cause these to move from one place to another through different loads. No, it's a vocab word, I think. Circuits. Good. Circuits. Let the record show that Streety even found that before he knew that I was writing it up on the board, so good job. And a circuit is you can kind of think of it as a way that human beings build something to force electrons to flow as we want them to. So we might have a battery. I've drawn a battery. This is the symbol for a battery. And a very simple circuit would be a battery with a light bulb on it. This is the light bulb. That's the symbol for a light bulb. This is the battery. And the electrons, as they flow through this wire, which is just the lines, from the battery, from one end of the battery to another, go through this light bulb, jimmy around with the materials in the light bulb, specifically the filament, and the light bulb lights up, right? This is called a load. Something that has a function because of an electrical circuit is called a load. And the math that we do with this circuit is called Ohm's law. Ohm's law. And it's given by this equation, V equals IR. And this is the main math. This is the main math for the chapter. What has to be true for this wire? What do we build wires out of largely? Copper, yes, that's specific. But yeah, a conductor. We build them out of an electric conductor. Last chapter we talked a little about thermal conductors, those objects that conduct heat, and now we're talking about electric conductors, those objects that conduct electricity. And so, and by the way, what do we call an object that doesn't do that or that resists that? An insulator, yeah. So we have here voltage, V is voltage. I is current, what your old-timer grandpa or uncle or someone when they were dealing with electricity might call amperage. And then R is what we just said for an insulator, resistance. And we measure resistance in the unit ohms, named after the same guy that Ohm's law is named after. Current we measure, as I said, amperage is measured in amps, amperes, and voltage is measured in volts, V. So voltage measured in volts, amperage measured in amps, or current measured in amps, and resistance measured in ohms. And this is a really neat equation because it's given to us in as what I would call the raw equation as straight multiplication, and so it's pretty easy to manipulate. If we want to get I by itself, what do we have to do? Yeah. Divide both sides by R, so we get V over R equals I. If I want to get R by itself, I have to divide both sides by I, so I get V over I equals R. And so it's a pretty easy equation to use in manipulation. And these units, I guess at this point you'll just have to kind of trust that they work out to equal each other. They are based on SI base units. Amperage is a SI base unit. Voltage, I can't remember, and ohms, I can't remember, but they end up being things like amperage over square meter or something like that. But anyway, all of that to one side, this is the math you'll be doing. And so we can measure if we know that this is a 9-volt battery, for instance, and we know that the resistance of this light bulb is 1 ohm, well, we can very easily, we won't do it on the video, but we can very easily find what the current going through that wire is, right? Current is the flow of electricity. Current is the flow of electricity. Voltage we often think of as like the storage of electrons. This battery holds 9 volts of electrons. And then as they're released through the light bulb, they flow, and that's measured in current. And how easy it is for them to flow is the resistance. And so you can see the relationship between these. The higher this resistance is, for a given voltage, we'll have a lower current, right? The lower the resistance is, for a given voltage, we'll have a higher current. That's the mathematical relationship among all those things. The other part, let's go rewind all the way back to the front. The other part of electromagnetism is what? Magnets. And we'll talk about not only magnets themselves, but also how magnets and electricity are related in the next chapter. But for now, do you have questions about kind of the two kinds of electricity or the math to do with current electricity? Okay. How will you practice the math? You have a worksheet and a chapter review.